Here's a matrix B with entries negative 1, 1, 1, negative 2. Its determinant equals positive 1. Quick question, is B positive definite? Tempting to say yes. But both eigenvalues turn out to be negative. The determinant lied. Today we'll cover 3 honest tests for positive definiteness, and one of them is shockingly fast. First, the definition. A symmetric matrix, meaning it equals its own transpose, is positive definite when all of its eigenvalues are strictly positive. Why should we care? In differential equations, the signs of eigenvalues determine stability. In optimization, a positive definite Hessian signals a local minimum, so we constantly need to know the signs of eigenvalues, often without actually computing them. And here is the catch. Solving the characteristic polynomial for a 5 by 5 matrix is brutal. For a 100 by 100 matrix, it becomes iterative and slow. We need shortcuts that reveal sign information without producing the eigenvalues themselves. There are 3 equivalent tests that detect positive definiteness. Test 1 is eigenvalues. This is the definition itself. All eigenvalues must be positive. The drawback is that computing eigenvalues is expensive. Test 2 is pivots. Run Gaussian elimination on the matrix. The pivots are the diagonal entries that appear during elimination. If every pivot is positive, the matrix is positive definite. This costs all the n-cubed operations, which is fast. Test 3 is leading sub-determinants, also called leading principal minors. You take the upper left 1 by 1 block, then the 2 by 2 block, then the 3 by 3, and so on, all the way up to the full matrix. If every one of these determinants is positive, the matrix is positive definite. For small matrices, this is the fastest test of all. These 3 conditions are mathematically equivalent. Any one of them implies the other 2. Let's run all 3 tests on a real matrix. Take A with entries 5, 2, 2, 3. It's symmetric, which is good. Start with the sub-determinant test. The 1 by 1 leading minor is just the top left entry, 5. That's positive. The 2 by 2 determinant is 5 times 3 minus 2 times 2, which is 15 minus 4 equals 11. Also positive. Both leading minors pass. Now on to pivots. The first pivot is 5. The product of the pivots equals the determinant, 11. So the second pivot is 11 over 5. Both positive. 2 tests down, 2 check marks. The matrix already qualifies as positive definite, but let's confirm with eigenvalues to see all 3 angles agree. Now for the eigenvalue test. Instead of finding eigenvalues directly, we use 2 shortcuts, the trace and the determinant. The trace is the sum of the diagonal entries, 5 plus 3, which equals 8. The determinant we already know is 11. So the characteristic polynomial is lambda squared minus 8 lambda plus 11 equals 0. Applying the quadratic formula, lambda equals 8 plus or minus the square root of 64 minus 44, all over 2. That simplifies to 4 plus or minus the square root of 5. Numerically, the square root of 5 is about 2.24. So the eigenvalues are roughly 6.24 and 1.76. Both are positive, so the eigenvalue test confirms positive definiteness. All 3 tests agree. Now here's something worth noticing. The pivots, 5 and 11/5, are not the eigenvalues, 4 plus or minus root 5. They're genuinely different numbers, but they have the same signs. Both pivots positive, both eigenvalues positive. That's the pivot signs theorem. Pivots and eigenvalues need not match in value, but their signs always agree. Now back to the trap from the opening. We have matrix B with entries negative 1, 1, 1, negative 2. Let's compute the determinant carefully. For a 2 by 2 matrix with entries A, B, C, D, the determinant is a times D minus B times C. So for B, it's negative 1 times negative 2 minus 1 times 1. Negative 1 times negative 2 is positive 2. 1 times 1 is 1. So the determinant equals 2 minus 1, which is 1. A positive determinant looks promising, but now check the 1 by 1 leading minor. That's just the top left entry, -1. Already negative. The matrix fails the sub-determinant test immediately, so B is not positive, definite. Let's confirm with eigenvalues. The trace of B is -1 plus -2 equals -3. The determinant is 1. So the characteristic polynomial is lambda squared plus 3 lambda plus 1 equals 0. Solving with the quadratic formula, lambda equals -3 plus or minus the square root of 5 all over 2. Numerically, that's about -0.38 and a -2.62. Both roots negative, confirming B is not positive definite. The lesson here is crucial. A positive full determinant only tells you there's an even number of negative eigenvalues, possibly 0, possibly 2. You must check every leading minor. This is why every leading minor must be checked, not just the last one. The signs cascade through the sequence. If the 1 by 1 minor is positive, but the 2 by 2 flips negative, you've caught a sign change that the final determinant alone would hide. 2 more cautions before we move on. First, symmetry is required. Without it, eigenvalues can be complex, and the equivalence between positive definiteness and positive eigenvalues breaks down. Always verify that A equals A transpose before applying these tests. Second, pivots and eigenvalues are not the same numbers. They are related by the pivot sign theorem. For symmetric matrices, the number of positive pivots equals the number of positive eigenvalues. Same signs, different values, don't conflate them. Step back and see the structure. Positive definiteness is a single property visible from 3 angles. Algebraic, the eigenvalues. Computational, the pivots from elimination. Structural, the leading sub-determinants. Same truth, 3 windows. Computationally, the difference matters. Eigenvalue computation for an n by n matrix is iterative with no closed form for n at least 5. Pivot computation through elimination is order n cubed and direct. For a 2 by 2 or 3 by 3 matrix, leading sub-determinants are fastest of all, just 2 or 3 small determinants. For a 100 by 100 matrix, you run elimination once and inspect the diagonal. No iteration, no characteristic polynomial. Where this leads, positive definite matrices are the matrix analog of positive numbers. They define energy functions, guarantee unique minima in optimization, and certify stability of dynamical systems. 3 tests, 1 truth, and now you can apply whichever one fits your problem.